So this is question number 6. What is degree of reaction in turbo machinery? So here I would like to introduce you one terms that usually comes out in turbo machinery. So normally sometimes we ask about the definition of degree of reaction. So degree of reaction here is actually it is showing the efficiency of turbine. So this is the meaning of a degree of reaction. And this is actually related to the next chapter, which is the tilted wheel. So let's say the question is, what is the degree of reaction in turbo machinery? So in turbo machinery, degree of reaction or reaction ratio R is defined as the ratio of the static pressure drop in the rotor to the static pressure drop in the stage, or as the ratio of static enthalpy drop in the rotor to the static enthalpy drop in the stage. So here the meaning of the rotor and the stage here is actually showing you the inlet and the outlet. So the rotor means the blade, so and the stage means at the output, something like that. So degree of reaction is an important factor in designing the blades of a turbine, compressor, pump, and other turbo machinery. It also tells us about the efficiency of machine, and it's used for proper selection of a machine and it others for a required purpose. So various definitions exist in terms of enthalpy, pressure, or flow geometry of the device. In case of turbine, both impulse and reaction machine, degree of reaction is defined as the ratio of energy transferred by the change in static head to the total energy transferred in the rotor. So I think the last sentence here, maybe it's clear the idea of degree of reaction. So actually it is show the efficiency. Okay, because in real world, in turbo machinery, sometimes they will use the idea of degree of reaction. Okay, there is something like power in turbine. So in calculation, we may use the idea of head of pump or head of turbine. But in common works, maybe people will talk about power. So this is about the common terms and the specific term that used in calculation. Okay, if we see the calculation is the degree of reaction, it is actually the static pressure drop at runner over total energy transferred. So and then the static pressure drop, okay, the energy here is actually is this one. You could see that this is actually the head, the difference of pressure head, and this is the difference of velocity head, and the E here, if you see this equation, it show the head of turbine. Okay, it might be P1 minus P2 because head of turbine is located at the outlet. So if we bring the P2 here and the V2 here, so P2 and V2 will have positive sign. So means that the E is actually come from the output. So head of turbine is at the output. So head of pump is in the input side. The head of turbine is at the output side. Okay. So and then the static pressure. So we have a pressure term here. So and then if we rearrange the equation, so we will have this one. So and then what we could do is we divide the static pressure drop here with the total energy. So and then we could have this term. Okay, so this might be the final term, the relation between the velocity and the energy. Okay, sometime last time might be 3 years back. Okay, so we asked students to prove the equation for degree of reaction. So I hope student could at least remember this step and then do the derivation in the exam. Then To get the maximum energy transfer, the blade must rotate at about half the velocity of the gas jet velocity. By definition, the impulse turbine has a degree of reaction equal to 0. So, and then here it is actually the statement for the impulse turbine. Later on in the next chapter, we will derive the idea of about half the velocity of the gas jet velocity. So this is the idea, because in impulse turbine, so we don't have the degree of reaction. So